Have you ever really stopped to think about what's happening when you look in a mirror? I mean, it kind of feels like a little bit of magic, right? But it's not. It's just pure physics. Today, we're going to dive into the science of reflection. It's the fundamental principle that explains every single mirror you've ever looked into and a whole lot more.
But first, let's start with a really simple question. You've probably never even thought to ask it. Why does a mirror give you this perfect, crystal clear image of yourself, but a painted wall, which, by the way, is also bouncing light off of it, shows you nothing at all? It's one of those everyday mysteries, and by the time we're done here, you are going to know the answer.
And here you can see it perfectly. On the left, you've got that sharp, clear image from a mirror. But on the right, just a wall, a textured surface. It's the same light, it's the same pair of eyes looking at both, but the results couldn't be more different. So what is the secret?
All right, to solve this little mystery, we need to get back to basics. We have to understand what it even means to see something. And when you boil it all down, seeing anything at all comes down to one simple idea: reflection. So what is reflection? Well, at its core, it's incredibly simple. It's just the bouncing of a wave, in our case, a light wave, off of a surface. Seriously, think about it like throwing a tennis ball against a wall. The ball hits the wall and it bounces back. Light does the exact same thing.
And you know, just like that tennis ball, light doesn't just bounce back randomly in any old direction. Nope. It follows a very strict, very predictable rule. It's a rule that governs every single reflection in the entire universe.
Okay, so this diagram breaks down that universal law. The light ray that's coming in is called the incident wave. The one bouncing out is the reflected wave. And that dotted line, see that? The one that's at a right angle to the surface, that's called the normal. And this whole law is all about the angles of those two waves. And here it is. This is the whole secret. The angle of incidence equals the angle of reflection. Or, to put it simply, the angle the light comes in at is the exact same angle it goes out at. This one little rule is the key to absolutely everything we're talking about today.
All right, so you might be thinking, if every single reflection follows that exact same law, how on earth can it create such different results? Well, let's go back to our mirror and our painted wall.
This is where the texture of the surface becomes so important. Look, on a super smooth surface like a mirror, all the light rays come in parallel, they all hit the surface at the same angle, and so they all bounce off at the same angle, staying perfectly parallel. But on a rough surface, even one that looks smooth to us, it's actually made of millions of tiny little surfaces all facing different directions. So while each individual light ray still follows the law perfectly, they all end up scattering in a million different directions. And this table just sums it up. Regular reflection, that happens on smooth surfaces, it keeps the light rays parallel, and boom, you get a sharp image. Diffuse reflection, that's for rough surfaces, it scatters the rays all over the place, and you get no image at all. And that, right there, is why you can see yourself in a mirror, but not on a painted wall. Mystery solved.
So now that we've cracked that code, let's take a look at how different kinds of mirrors use this principle, starting with the one you and I use every single day.
This is a plane mirror, and plane is just a fancy word for flat. It's just a mirror with a perfectly flat, reflecting surface. You know, your bathroom mirror, the one on your closet door, those are all plane mirrors.
So how does it actually make an image? Well, light from you bounces off the mirror and shoots into your eyes. But here's the trick. Your brain is wired to think that light always travels in perfectly straight lines. So it traces those reflected rays backwards in a straight line to a point where they look like they're coming from. And that point is behind the mirror. Because the light isn't really coming from there, we call it a virtual image.
And the images you see in a plane mirror always have these four things in common. They're virtual, meaning you can't project them on a screen. They are upright, thankfully not upside down. They're the exact same size as the real object. And of course, they are left-right reversed. It's why when you raise your right hand, your reflection raises its left.
Okay, but what happens when we mess with that flat surface? What happens when we start to curve the mirror? Well, this is where reality really starts to bend, and we get all sorts of cool, weird effects.
First up, we've got the concave mirror. The easiest way to remember this one is that it curves inward, like a cave. Or just go grab a spoon. It's the side you'd eat soup from.
So unlike a flat mirror, that inward curve makes parallel light rays bounce inward and converge, or, come together at one single spot. We call that the focal point. And this ability to focus light is what makes these mirrors so powerful.
And here's where the magic really happens with concave mirrors. The kind of image you get completely changes based on how close you are to the mirror. It can be real or virtual, upside down or upright, magnified or smaller. It all depends on your distance. This is exactly how a makeup mirror works. It's concave, and when you get up close, it magnifies your face.
Now let's flip that spoon over. That's a convex mirror. It's the one that curves outward, towards you. And as you might guess, it does the exact opposite of a concave mirror. Instead of bringing light rays together, that outward curve makes the light rays spread apart, or diverge, after they bounce off.
Now, unlike that complicated concave mirror, convex mirrors are super consistent. The image you see is always virtual, it's always upright, and it's always smaller than the actual object. And that ability to shrink a huge area into a tiny image is why they're so useful for things like security mirrors in stores or the side view mirrors on your car. They give you a much wider view of what's behind you.
So there you have it. We've gone from a simple law about angles all the way to the wild, funhouse effects of curved mirrors. We've seen how reflection literally shapes the world we see. And it's not just in mirrors, it's in every single surface that light bounces off of to reach our eyes.
And that kind of brings us to a final thought. Once you understand these rules of reflection, you start seeing them everywhere. So the next time you catch your reflection in a shop window, or on the back of a spoon, or even in a puddle on the street, you'll know exactly how that image got there. So the real question is, what else around you is bending reality with light?